We are live.
Okay, good morning. I am Mar Carretero Castrillo. I have just started my PhD in September with Mar and Jose Maria Paredes. And today I will present you one of the projects of my PhD, that is the search for new gamma ray binaries using Gaia. So, first of all, let me say that this is a high energy astrophysics project which takes benefits of the use of Gaia data. So I would like to thank the Gaia people who has helped us during these months. Okay, let's start. I will introduce what are gamma ray binaries. Then I will present the motivation of this project and how we have obtained the results. And I will finish with some conclusions and the future steps of this project. So, we have new facilities since 2005 to observe the sky in GV and TV mission. Some of these facilities are the Fermi-Lab satellite and the MAGIC and HESS Cherenkov telescopes. On the left, we have an image of an all-sky image taken by Fermi at GeV energies, and on the right, we have a galactic plane survey taken by HESS at TV energies. So, with these new facilities, we have discovered new types of gamma ray sources, and in particular, gamma ray binaries. So, what are gamma ray binaries? We have a binary system that has a massive star and a compact object. This compact object could be a pulsar or a black hole. So these systems have the maximum of the non-thermal emission at gamma ray energies. In this figure, we have the luminosity as a function of the frequency of one of these systems. Here we have the thermal contribution from the massive star, and the other contributions are of the non-thermal emission from the binary system. We can see that these systems have broadband multi-wavelength emission from radio to gamma rays. We only know 9 of these systems, and the nature of the compact object is only confirmed in 2 of them, that is a pulsar. They don't have clear accretion signatures, and they have very different orbital configuration in periods and eccentricities. Here we have a table of the gamma ray binary system that are known. We can see that the spectral type of the massive star are OB type. They have a wide range of orbital periods, and they are typically located at a few kiloparsecs, except for the one located at the Large Magellanic Cloud. So, one possible scenario to explain the observed emission is the non-accreting pulsar. In this scenario, we have a massive star and a compact object that is a pulsar. This pulsar has a relativistic wind that is here indicated in green. This relativistic wind interacts with the wind of the stellar companion and forms a shock. In fact, we have 2 shocks, the shock between both winds and the shock, the Coriolis shock. So, in the interaction between both winds, the particles are accelerated at very high energies. And due to the magnetic field, they emit synchronous radiation from radio to X-rays, and also these accelerated particles interact with the optical photons from the massive star and emit gamma rays by inverse contact. However, we don't know all about these systems. There are many open questions. Some of them are dual gamma ray binaries contain pulsar, why they only have all B stars, what is the real population of these systems in our galaxy, does this population fit the binary stellar evolution codes, what will CTA see, do all nearby objects, or do we know all nearby objects or just the tip of the iceberg? Are the known ones representative of the population, and what are the relevant physical parameters to produce the GeV and TeV emission? These are just some of the open questions, but we need to discover more gamma ray binaries to try to answer some of them. So now I will explain what is the GeV and its effects in binary orbits. Imagine that we have a binary system with two massive stars. They are orbiting around a center of mass. After a while, the more massive star evolves faster and explodes in a supernova and forms a compact object. After this explosion, the system will remain bound if less than half of the mass is lost. The next step is that because of the conservation of linear and angular momentum, the supernova ejecta and the binary system will move in opposite direction. So the orbit will change, and we will have a binary system that can become a runaway, because after this kick, the system can acquire very high velocities. A runaway system will be a system with peculiar velocities between 30 to 200 kilometers per second. So this leads to the motivation of our project. Since kicks can transform binary system in runaways, we can have some gamma ray binaries with extremely high peculiar velocities. So in fact, here we have a table. We can see here that some of the gamma ray binary systems are runaways. For this reason, we want to search for runaways in catalogs of galactic massive stars. With this, we will obtain a list of gamma ray binary candidates that we will later study in detail. This method should allow us to discover additional gamma ray binaries with a different selection bias than previous method, because previous methods basically consist on looking for gamma ray emission. So the first step to find these objects will be to select the data. We have chosen the GOES catalog, that is a galactic catalog of O-type stars, and we have cross-matched with the second data relief of the astrometric mission Gaia. We have applied these filters to guarantee a good quality of the astrometric data, of the proper motions, positions, parallaxes. After applying these filters, we have ended up with a catalog of 366 stars. So this is what we have called the GOES Gaia DR2 catalog. These are how the sources look of this catalog. We have stars with magnitude from 6 to 12.5, and they are located at distances from 0.5 to 6.5 kiloparsecs. We can see here both histograms. Here we have a projection in galactic coordinates of the location of these sources. Here in the middle we have the galactic center, and this is the galactic plane. In the x-axis we have the galactic longitude, and in the y-axis we have the galactic latitude. So we can see that our sources are located 3 degrees above and below the plane. So once we have the data, now we need to compute their velocities. We have used the Galactocentric coordinate system. I will explain how it works. Here we have the galactic center, and imagine that here we have a star. This system has the x component directed towards the galactic center, the y component directed in the sense of the galactic rotation, and the theta component perpendicular to this plane. And the u, v, and w components are the velocities. So to compute the velocities, we need to take into account that the galaxy is rotating. So we need to choose a galactic rotation curve. We have which is defined as the linear velocity as a function of the galactocentric distance. that is this R that we have here, because the galactocentric distance is the distance from the galactic center to the star. So with this galactic rotation curve, we can infer the velocity of a star given its galactocentric distance. In addition, we have assumed cylindrical symmetry to compute our velocities, as observation favor this hypothesis. So in this figure, we have again here the galactic center. Here is located the sun, and imagine that we are observing a star from the sun. So we want to compute this the velocity, the peculiar velocity of these stars from the sun. For this, we have to start from the local standard of rest system. Okay, this is a system that is located at the position of the sun. So first, we compute these velocities from here, and then we transform these velocities to the regional standard of rest. That is a system located at the position of the star. For this, we need a galactic rotation curve, and we have used the one from Wright et al. 2019. And we also need radial velocities. However, the second data release of Gaia does not provide with enough quantity of radial velocities. So we have computed trigonometrically by taking into account the galactic rotation curve. So for this reason, we have defined a new reference system because we want to get rid of the radial velocity contribution. This system is composed of the tangential velocity component, which is a velocity in the plane of the sky and parallel to the galactic plane. The second component is the radial velocity, which is defined along the line of sight direction, and the third component is the perpendicular to this plane. So from now on, we will work only with the two-dimensional system of the tangential velocity and the perpendicular velocity. So here we have the results. As I said, we have worked with these two velocity components. Here we have the histogram of each velocity component. We have computed this histogram with a beginning of 2 kilometers per second. And in the middle, we have a plot of the perpendicular velocity as a function of the tangential velocity. So what do we have here? We have that most of the stars are located at the 0, velocities, but they have some dispersion. And in fact, we can see that there are some stars with clearly high velocities. So, since these histograms have a Gaussian shape, we have applied a Gaussian fit, and we have obtained a standard deviation of about 9 kilometers per second, that are the typical values for young stars. Now we have the velocities, and we need to establish a criterion to determine which stars are runaways. So we have defined a 3 sigma ellipse that is here in red. So with this ellipse, we will classify the stars that are inside this ellipse as field stars, while the stars that are outside this ellipse, taking into account the uncertainties, will be classified as runaways. So applying this method, we have obtained 82 runaway stars. Here we have the same plots, but with the runaways in red and with the field star in blue. We have different points, empty points and red points filled, and this is because we have compared from our runaway stars, which were found also by Maiza et al. In 2018. At that point, we should keep into account that the runaway stars are affecting this fit, because they don't belong to this distribution. So for this reason, we have applied a clipping method, which is an iterative method to exclude the stars that don't belong to this distribution. And we have applied here, if we have focus now in this table, we can see that here we have each iteration, and in each iteration we have computed a Gaussian fit, we have obtained a mean values and a standard deviation, and we have excluded a number of stars. So we can see that in each iteration we are improving the Gaussian fit because the standard deviation are decreasing. So after applying this clipping, we have ended up with 6 more runaway stars. So after the clipping, we have a total number of 88 runaway stars, which is the 24% of the Ghost Gaia DR2 catalog. The peculiar velocities of these stars, of these runaways, are between 30 to 230 kilometers per second, and if we compare them with the peculiar velocity of the gamma ray binaries that are runaways, we can see that they are similar, between 26 and 142 kilometers per second. We have also tried to look for the gamma ray that are runaways in our catalog, and we only found the LS5039. It was the only source that was contained in our initial catalog, and we can see that with our method we have also classified this gamma ray binary as a runaway, so our method works. I have located here this gamma ray binary. We can see also in this projection, again in galactic coordinates, the location of this gamma ray binary here. So we have also computed the galactic latitude, the mean of the galactic latitude and its standard deviation of the field stars and the runaways, and also the height with respect to the galactic plane. And we can see that the field stars are more located around at the galactic plane, while the runaways are a bit more far away from this galactic plane. So once we have computed all this method with Gaia DR2 data, we have computed this whole method with the Gaia EDR3 data. We can see that when we have cross-matched the ghost catalog with the Gaia EDR3 data, we have obtained a larger catalog with 407 stars, and we have found that the errors and the standard deviation of the perpendicular velocity component have decreased. After applying all the method and the clipping, we have ended up with 111 runaway stars, which is the 27% of the Ghost Gaia EDR3 catalog. And the peculiar velocities are between 16 to almost 30 kilometers per second. We have also tried to look for the LS5039 with method, and again we have also classified this as a runaway. So to finish, we have seen that gamma ray binaries with an O-type star present high peculiar velocities. We have analyzed a sample of early type stars to search for new gamma ray binaries, and we have found 88 runaway stars with Gaia DR2 data and 111 runaways with Gaia EDR3 data. And the key point is that some of these runaways could be gamma ray binaries. So as a future work, we want to conduct a similar study with big and B star catalog. We're going to publish this methodology and the obtained results, and the second part of this project will be to search for non-thermal emission in other catalogs and prepare observations in radio velocity, photometry, radio X-rays, and as a final step, we also want to serve with MAGIC and CTA. So, take-home messages. Searching for runaways can lead to discover new gamma ray binaries. Okay? We have found 111 runaways with Gaia ADRC data, and now we have to study the sources to try to detect new gamma ray binaries. So I have said currently there are only 9 of this system known, and I want you to pay attention to these numbers because we have 111 candidates to be gamma ray binaries, and actually we only know 9 of them. So amazing, isn't it? I should confess that I am quite excited with the numbers. That's all. Thank you for your attention.
Okay, thank you very much. Mar, it is time for questions.
So yeah, you showed that most of them are O or B E stars with a well, the known objects are pulsars, right? So do you know, or do we know something about the origin of these systems? Because it seems like the O star is then more massive than the progenitor of the neutron star.
Sorry, I couldn't listen you the last part. Could you speak a bit louder?
Yeah. So it seems like the O star is more massive than the mass of the progenitor of the pulsar. So how does this system form? Do we know how such a gamma ray binary forms?
How this gamma ray binary forms? Why? Because why massive stars? Are you saying?
Well, why? I mean, it seems weird to have the star that is still on the main sequence to be more massive than the progenitor of the neutron star, because you would have expect the O star to be gone before you make the neutron star. So is what is the consensus formation picture here? That this O star is has accreted mass from a donor or from the donor?
Not actually. We think that this massive star is a transition between the gamma ray binary into the X-ray binary. So we have first a massive star, and in the actual scenario, we don't think that the pulsar is accreting massive mass of this star. Is this what you answer?
No, well, maybe you can talk a bit more about
Yes.
yeah, thank you.
Sorry, Jessica.
My question is on the map of tangential velocity against the perpendicular velocity. My question is, these stars are very young. These stars, as you mentioned, they are in the galactic plane. They are rotating in the plane formation from the disk, so from the gas. Could it be interesting to have a higher priority to the sources that are in fact with the kick moved perpendicular to the plane? Because you used standard deviation, but I understood it's Gaussian, has no priority in the vertical direction. Is that true that the vertical direction, if you find something, it means that probably the kick is more probable? This is one question. The other one is, just at the beginning we said that my runaway should be in terms of velocities from 30 to 200 kilometers per second. I understand that you are following that, considering the observational constraint, you know, from the ones that they are already known. Is there any theoretical constraint on the velocities, considering the mass of the two systems, how the mass, the wind, blah blah? Are some theoretical analysis yet done to constrain this kinematic range, where to look for? Because this is the new capacities of Gaia. These two questions. Thank you.
Okay, so the first one, yes, we are also, in fact, we are interested in the stars that are a bit more outside this plane, because as we can see here, the runaway stars are the ones that present higher latitude and higher height with respect to the galactic plane. And this could be produced by the kick, because all the stars are moving with the sense of the galactic rotation, but if we found a star that is higher from this plane, this could be produced by the kick. So we are very interested in these sources. And the second one, theoretic range of peculiar velocities, I actually don't know. So if someone knows, but
Mar, can I ask, how deep are you reaching with your catalogs? I mean, this ghost catalog, what's the magnitude limit more or less, and so what distances are you covering?
Okay. This histogram of the ghost catalog combined with the Gaia DR2 data. We have distancing from 6 to 12.5 kiloparsecs.
And then when you compute velocities, you're talking kilometers per second, and so the error in distance here can be important. Do you take these errors into account when you select these cuts in runaways? For
Yes,
this,
yes, sure. Because the error in distance is also an important contribution. So when we define this ellipse, we have to take into account the individual uncertainties of each star. So in fact, if we look to this classification, we can find in this region some field stars and runaway that are in the same region, and this is because maybe this star have a larger uncertainty than the other that is a runaway.
Okay, thanks. Yeah, maybe we can talk more later.
Okay.
Yeah, if there are more questions, I suggest you to ask these questions during the coffee break without coffee, unfortunately. Okay, let's move to the next speaker. Thank you very much. Thank Mar again.